Transition properties. Firstly, atomicity. All the operations of a transition must be completed. If not, the transition is aborted. If a transition T1 has 4 SQL requests, all 4 requests must be successfully completed. In other words, a transition is treated as a single indivisible logical unit of word. Second, durability. Once transitions are committed, they cannot be undone. Third, serializability. Concurrent execution of several transitions yields consistent result. Multi-user database subject to multiple concurrent transitions. For consistency, permanence of database consistent state. A transition takes the database from one consistent state to another consistent state. When a transition is completed, the database must be in a consistent state. If any of the transition parts violates an integrity constraint, the entire transition is aborted. Last, isolation. Data used during transition cannot be used by second transitions until the first is completed. So atomicity, durability, serializability, consistency, and isolation. Common problems with concurrent transitions execution. 3 main problems are loss, update, uncommitted data, and inconsistent retrieval. Loss update is 2 concurrent transitions update same data element. One of the update is lost, overwritten by the other transition. Uncommitted data is 2 transitions executed concurrently. First transition roll back after the second already accessed the uncommitted data. First transition roll back after second already accessed uncommitted data. Inconsistent retrieval is first transition access data, second transition alter the data, first transition access the data again. Transition might read some data before they are changed and other data after change, which yields inconsistent result. Loss update example is the product stock is 100, T1 read stock to sell 10 items, calculate 90, T2 read stock 100 to sell 5 items, calculate 95. T1 save 90, T2 quickly save 95, result become 95. T1 sale is wiped out. Uncommitted data example is T1 adds 200 deposit, changes balance to 700. T2 reads balance C700 and approves 650 loans. Because funds look sufficient, T1 fears and rollback. T2 approve on loan based on the dirty uncommitted money that never exists. So this is uncommitted data where 2 transitions executed concurrently. First transition rollback after second radio access uncommitted data. Inconsistent retrieval example is T1 reads account 100, read account A100 while T1 moves to next account. T2 transfer 50 from A to B, A balance 50, B balance 250, and commit. T1 reads account BC updated 250, T1 adds is finding 100 plus 250 and report total of 350, which is incorrect and inconsistent. Log. First label is database label log. Entire database is log, preventing the use of any tables in the database by transition T2 while transition T1 is being executed. For example, T1 uses property database. Log is the whole database to perform maintenance. If T2 wants to update the customer record, T2 cannot use property database and must wait until T1 release database log. If T1 log is the whole, T2 cannot access. Additional explanation is it's best for administrative tasks like upgrading database software, restoring backup, or migrating schema changes. Extremely safe for maintenance but terrible for performance if users actively try to use the app. Second level is table level log. Entire table is log, preventing access to any row by transition T2 while transition T1 is using the table. If a transition requires access to several tables, each table may be logged. However, 2 transitions can access same database as long as they access different table. For example, in T1, use an update table branch. In T2, not use table branch but use table stuff. T2 cannot update table branch if T1 is logged. Additional explanation is it is best for both data loads or altering table structure. It has low overhead for database, only track one log but creates massive bottlenecks in high traffic application. Third level is page level log. Entirely this page is locked. For example, in T1, use table branch with table in page 1. In T2, use table branch tables in page 2, not in page 1. Another example is table has 100 pages. T1 lock page 12 only. T1 can use page 1 to 11 and 12 to 100. So when one record on the page is updated, entire page is locked to prevent other users from modifying data. This helps improve database performance, but it reduces concurrency. Fourth level is row level lock. Each entire row is locked allows concurrent transitions to access different rows of same table, even if rows are located on same page. Lock is on a single record. For example, T1 locks customer record ID equal 101. If T2 wants to update customer record ID equal 101, it must wait. If T2 updates customer record ID equal 102, it can proceed immediately. Fifth level is field level lock. Entire attribute is locked. It allows concurrent transitions to access same row and requires use of different fields or attributes within the row. Entire attribute is locked. It allows concurrent transitions to access same row and requires use of different fields attribute within the row. For example, T1 locks the full number field of customer ID equal 101. T2 cannot update. For example, T1 locks the full number field of customer ID equal 101. T2 cannot update the same full number field unless it wants to update the email field of customer ID equal 101. It can proceed. Example, T1 locks the full number field of customer ID equal 101. T2 cannot update same full number field unless they want to update the email field of customer ID equal 101. It can proceed. Additional explanation is it allows highest flexibility but expensive to manage. Date lock is a condition that occurs when two transitions wait for each other to unlock data. It's possible only if one of the transitions wants to obtain an exclusive lock on the data item. There is no date lock condition can access. No date lock condition can access among shared locks. No date lock condition can access among shared locks. Three techniques to control date lock. Firstly, prevention. Secondly, detection. And thirdly, avoidance. Prevention, detection, and avoidance. Low probability of date lock detection recommended. High probability prevention recommended. The full right technique is only transition lock is updated. So firstly, identify last checkpoint. Secondly, if transition committed before checkpoint, do nothing. Thirdly, if transition committed after checkpoint, use transition lock to redo the transition. Fourthly, if transition had rollback operation, do nothing. Then for the write-through technique, database is immediately updated by transitions operations during transition execution. Firstly, identify last checkpoint. If transition was committed before checkpoint, do nothing. If transition was committed after last checkpoint, DBMS redoes the transition using the after value. If transition had rollback or was left active, do nothing because no updates were made.